Hi everyone, welcome to the first example video for the Intro to Proofs series. And so these are going to occur between every lecture video. And they'll be based off of what was covered in the lecture video. So this is the first example video, so it deals with stuff covered in the first lecture video. Okay, so let's jump into it. So let's look at this first example. We want to write the following set listing the elements. So this set is given in set builder notation at the moment, and we'd like to change this to maybe something called a roster notation. So let's just start by focusing on this inequality that is defining the entries here. So let's notice our inequality is 9x minus 4 is less than 45. So let's solve that inequality first, and then after solving that inequality, we will take care of the fact that we're really just looking at integers here. Okay, so that inequality, absolute value of 9x minus 4 is less than 45, is equivalent to the compound inequality, which is minus 45 is less than 9x minus 4, which is less than positive 45. And now we just do this kind of as normal. So we'll add 4 to all of the sides. That'll give us something like minus 41 is less than 9x, which is less than 49. And now we'll divide by 9. So that'll give us minus 41 over 9 is less than x, which is less than 49 over 9. Okay, then you might write this in interval notation if you were like in a pre-calculus type class. But since we're in this intro to proof writing class, what we'd like to do instead is write a list. So now taking advantage of the fact that x is an integer, and these are both non-integers. They're rational numbers, but they're non-integers. We say that x has to be bigger than or equal to, that'll be negative 4, but it has to be less than or equal to 5. Great. And so we can easily list those numbers. We have negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. And that would be our final answer. So that would be us listing all of the numbers in this set. Okay, so let's look at another similar problem. Let's list the elements from the following set. So we have all integers x such that x squared minus 4x is less than 12. So we'll start by approaching this the same way. Notice this is equivalent to looking at x squared minus 4x minus 12 is less than 0. But in order to find out where it's less than 0, we probably want to find out where it's equal to 0. But here we can do this actually by factoring. Notice if we factor this as x minus 6 times x plus 2, we're good to go. So we get that x minus 6 times x plus 2 is less than 0. But like I said, we probably want to look at where it's equal to 0. So let's just recall that x equals 6 and x equals negative 2 are likely to be important points. So I'll put stars around those to say they're likely to be important points. And now we'll use a general pre-calculus approach here of test points. So let's take our number line. We'll pick our number line apart using these important points. So we've got negative 2 and 6. And then we'll pick test points in each of the regions split up by those two places. So 0 would be a good choice between negative 2 and 6. Over here, maybe we would choose 7. And over here, maybe we would choose negative 3. Okay. So now if we plug those into our expression, maybe right here, and look for if it's satisfied or not, that should give us some motivation for finding our final answer. Okay, so let's check the number 0 first. So 0 squared minus 4 times 0 minus 12 is less than 0, so this one is okay. So since that's okay, and that's really serving as a representative for everything between negative 2 and 6, that means we get to include everything between negative 2 and 6. So we might write that in interval notation, or we might graph that as an interval along the real line like this. And then later we'll take advantage of the fact that we're really within the integers. And now let's look at the others. So let's maybe look at 7. So if we take 7 squared, minus 4 times 7 minus 12. Well, let's see. That's going to give us 49 minus 28 minus 12. That's still positive. So that's not okay. And by not okay, I mean that is not satisfying our inequality here. So that means we wouldn't shade that portion in. And so similarly, we will not shade this portion over here in as well. Okay, so that means all of the numbers that we need will be integers between -2 and 6. So let's see, that'll be -1, 0, 1, 2, 3, 4, 5, like that. And I guess I should point out here that this is a strict inequality, which is why we do not include 2 or 6. Okay, so let's move on. So let's write the following set in set builder notation. So we've got the set containing 0, 3, 8, 15, 24, 35, and I guess I should say this should extend infinitely. So 35 ... So we've got an infinite set. So we need to look at the pattern. So perhaps we should try to fill in the next couple of terms first, and that'll give us some insight as to what the pattern is. So if we look at this a little bit, we notice that each of these numbers is 1 less than a perfect square. So we have 1 squared minus 1 is 0, 2 squared minus 1 is 4 minus 1, which is 3, 3 squared minus 1 is 8, 4 squared minus 1 is 16, so on and so forth. So notice this one right here is 6 squared minus 1, so the next number would in fact be 7 squared minus 1, or 49 minus 1, 48. Okay, so I think that's enough to write down what we have. So I would maybe write this as everything of the form n squared minus 1, where n is a natural number. Notice we want to write with natural numbers here, not integers, because if we used integers, we would also include the number -1, given that 0 squared minus 1 is -1. So this would be a nice final answer for this problem. Okay, so now let's look at this find the cardinality question. So finding the cardinality is finding the number of elements in a set. So this is a pretty funny looking set. It contains the number 1, but it also contains this crazy set here that contains the number 1, and it also contains a set containing 2 numbers, 2 and 3. And then finally, this crazy set also contains the set of all integers. So the set of all integers is most definitely infinite, but the cardinality of our larger set is not infinite. That's because it really only contains 3 elements. So let's write those 3 elements down. So those 3 elements are the following. We'll have the number 1, we'll have this set containing the number 1 and the set containing 2 and 3, and then our third element is simply the set of all integers. Okay, so what does that mean? That means our cardinality is, in fact, 3. Now let's look at this next one. We want to look for all natural numbers x such that x squared plus 6x is less than 21. So I think there are a couple of ways to do this. You could maybe solve this carefully to find some sort of interval and look at the natural numbers within that interval. But I think it's pretty easy to do this with just guessing and checking. So let's check x equals 1. So if you plug x equals 1 into this, you'll get 1 squared plus 6 times 1. That's equal to 7. That's less than 21. So yes, that is in our set. Now let's look at x equals 2. So that'll give us 2 squared plus 6 times 2. Okay, well that'll be 4 plus 12. That'll be 16. That's less than 21. So yes, 2 is also in our set. Let's look at x equals 3. So we'll have 3 squared plus 6 times 3. That'll be 9 plus 18. 9 plus 18 is 26. 26 is not less than 21. So this is not in the set. But now let's note if x is bigger than or equal to 4, then x squared plus 6x will be strictly bigger than 3 squared plus 6 times 3, which is strictly bigger than 21. So that means we cannot include anything bigger than or equal to 4. So that means in the end, this set only contains the number 1 and 2. But remember, we're looking for the cardinality. The cardinality of this set is 2. That's the number of elements in this set. Okay, moving on. So now we'll sketch the following set in the xy plane. So I like these quite a bit. So let's see, we've got all real numbers x, y put into a ordered pair, satisfying the inequality where x squared minus 3x is bigger than or equal to y. So let's start by graphing y equals x squared minus 3x. Notice we can factor that as x times x minus 3. So this is a parabola, and we have x-intercepts at x equals 0 and x equals 3. So I think we can get started just with that knowledge. So let's go here to x equals 0. That's one of our x-intercepts. X equals 3. That's one of our x-intercepts. This is an upward-facing parabola. So we get some sort of picture like this. And then we want all the y that are less than or equal to this. I think maybe it's a little bit more natural to rewrite this as y less than or equal to x squared minus 3x. So that means we need all y values that are below this. So that would be the shading that we want in this case. Okay, so we've got another one. Sketch the following in the xy plane. So we've got all points xy where x is a real number, y is a natural number, and y is less than or equal to x. Okay, so let's get going on this one. So let's make our coordinate plane here. Let's note that y has to be a natural number. So that means we need to focus on when y is something like 1, 2, or 3. And I think that's enough structure to give us an idea of what's going on in general. And then just to make this have some nice like symmetry, let's say we have x equals 1, x equals 2, and then x equals 3. Now let's work this out. So if x is equal to 1, the only natural number, which is smaller than 1, is 1, or smaller than or equal to 1. So that means y has to be equal to 1. And now if x is something over here, so if x is less than 1, then there's no natural number that is less than 1. So that means this is our kind of first occurrence of a point here. Now let's go over here to x equals 2. So there are two natural numbers that satisfy the inequality y less than or equal to 2, and those will be the number 1 and the number 2. And then likewise, there are three natural numbers that satisfy the inequality y less than or equal to 3, and those are 1, 2, 3. So there we've graphed everything, not in this set, but everything where x is a real number. Now let's fill in some of the missing parts. So what happens if x is like 1.5? So let's say it's right there. Well, the only natural number, which is less than or equal to 1.5, is 1. So that's the only y value we can take. And that's going to be true for everything between 1 and 2. So that'll fill in everything right here. Now, what about 2.5? So something right there. Well, there are exactly two natural numbers that are less than or equal to 2.5, and those are 1 and 2. That'll fill in these lines here and here. Okay. And as you can imagine, this is going to go infinitely in this direction. So what we'll get is like this kind of infinite staircase going up. So we'll have something up here as well, and so on and so forth. So that would be the final picture of this set. Okay, so now let's look at this problem with the power set. We want to find the following set, or write the following set by listing its elements. So let's do these one at a time. Let's first find the power set of the set containing 1 and 2. So that'll be the empty set, the set containing 1, the set containing 2, and the set containing 1 and 2. Recall the power set is the set of all subsets. Now let's look at the power set of the set containing 3 and 4. So again, that's going to be the set of all subsets. We'll have the empty set, we'll have the set containing 3, we'll have the set containing 4, and we'll have the set containing 3 and 4. So there we've got that. And now we need to take the Cartesian product of these two sets. So let's do that. We can start off with the ordered pair of the empty set and the empty set. So that's from taking the empty set from both of our sets. Then next we could have the empty set and the set containing 3, the empty set and the set containing 4, and finally the empty set and the set containing 3 and 4. And so that uses like all of the starting points where our first entry is the empty set. Okay, good. And then moving down, we could look at everything where our first entry is the set containing 1. So we'll have the set containing 1 and the empty set. So that ordered pair, the set containing 1 and the set containing 3, the set containing 1 and the set containing 4, and finally the set containing 1 and the set containing 3 and 4. Okay, then from here we can like move all the way down and keep going. We'll get 8 more total sets. And they'll look kind of like this. You'll have the set containing 1 and 2, and along with the empty set. So that'll come from something like taking this as our first entry and this is our second entry. And then you could also have maybe the set containing 1, 2 as the first entry, and then the set containing 3, 4 as the second entry. Okay, moving on. Okay, so now let's look at this related question where we do everything in the different order. We'll take the cross product first, and after taking the cross product, then we'll take the power set. So what we're looking at is the power set of, let's see, we'll have the set containing, it'll have 4 elements. Those elements will be like 1, 3, 1, 4, 2, 3, and 2, 4, taking entries from the first set or the second set as needed. And then from a fact that we saw in the lecture, we know there should be 2 to the 4 or 16 elements of this power set as well. So let's see what they are. So we could first have the set containing 0 elements. That'll be the empty set. And then we'll have 4 sets containing a single element. So you'll have the singleton 1, 3. So you might say, well, this has 2 elements, but it doesn't have 2 elements. This is an ordered pair, which is a single element. You have the set containing the ordered pair 1, 4. You have the set containing the ordered pair 2, 3. And then finally, the set containing the ordered pair 2, 4. So those would be 5 of our sets. Next, we can take all of the sets with 2 elements. So that'll be the set containing the ordered pair 1, 3, and 1, 4. That would be maybe a good choice. The set containing the ordered pair 1, 3, and 2, 3. Next, the set containing the ordered pair 1, 3, and the ordered pair 2, 4. Then we can move on to the set containing the ordered pair 1, 4, and 2, 3. The set containing the ordered pair 1, 4, and 2, 4. And I believe we have one more like this. And by like this, I mean set with 2 elements. And that'll be the set containing the ordered pair 2, 3, and the ordered pair 2, 4. Okay, there. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements so far. So now we need sets containing 3 elements, but I'll let you write those down on your own. They're actually easy to calculate just by looking at sets that do not include these elements. So we'd take all of the ordered pairs except 1, 3. That would be one of the sets. All of the ordered pairs except 1, 4. That would be one of the sets. All of the ordered pairs except 2, 3, that would be one, and all of the ordered pairs except 2, 4, that would be another set. And then finally, our final set will be the entire set. So that'll be 1, 3, 1, 4, 2, 3, and 2, 4. And then all in all, we should have 16 subsets. Okay, so now we've got another interesting one. We're repeating the power set. We have the power set of the singleton 1. So let's work inside to outside. So we'll start with the power set of, well, what are the subsets of the singleton 1? Well, the empty set is always a subset, and then the set itself, so the singleton 1 is also a subset. But now we're taking the power set of this 2-element set. This 2-element set has 2 different elements. One is the empty set and one is this singleton. So we should expect 4 elements. So let's see. We'll have the empty set, that's always a subset. We'll have the set containing the empty set, that's a singleton. We'll have the set containing 1. And then finally, we'll have the set containing the empty set and the set containing 1. So that would be our power set of the singleton 1. So let's look at all elements of the power set of this 4-element set. Remember that elements of the power set are, in fact, just the subsets. So that means X is a subset of 1, 2, 3, 4. And the condition we want to put on X is that X has the number 2 inside of it. Okay, so let's see. Well, the singleton 2 will be good. So that's one of them. And then you can have 2-element sets containing 2. So that'll be like 1, 2. We could have 2, 3, or we could have 2, 4. So those are all the 2-element sets containing 2. Now we want 3-element sets containing 2. So let's see, maybe 2, 3, 4 would be one of those. 1, 2, 3 would be one of those. And let's see, 1, 2, 4 would be another one of those. And then we'll need 4-element sets also containing 2, but that'll be the set itself. So 1, 2, 3, 4. Great. And then let's put braces around this whole thing, and that would be our final description of this set. Okay, so I hope you find this useful, these examples to work off the lecture videos, and that's a good place to stop.